Hello again, calculus students. This is a continuation of the video on vectors. Part B is going to be specifically related to the magnitude and direction of vectors, and I think this warrants its own little talk. So here we are, talking about the magnitude and direction of vectors. So, the next topic, we talked about the vector, for instance, the vector A, right? And I put this little thing above it to make sure that we know it's a vector. I can represent it like this. I could make a vector that goes 3, 4, -7, right? And that means that this vector, the x component is 3, the y component is 4, and the z component is -7. Right? It doesn't necessarily have a location. It could start anywhere and end anywhere, as long as the difference between the start and the end are 3, 4, and -7 for the x, y, and z coordinates respectively. All right, but I'm going to introduce a new topic now with the black pen that I'm going to call unit vectors. All right, what is a unit vector? Well, it's a little bit kind of like any other unit, such as 3,956 grams, or 54 centimeters, or 850 miles, right? What is this? This is the scalar part of it, the 3956, and the grams tells us 3956 what, right? 54, scalar number. Just 54 doesn't mean much to us until we say what is it. In this case, it's centimeters, or 850 miles. Now, in the vector world, we have 3 special unit vectors. Three special unit vectors. And as you might guess, the first one is I hat. All right, the little hat means that it's a unit vector. We'll talk about that. We could just call it is a vector, right? But it's a special vector. So if I write this in the angle bracket notation, it's 1, 0, 0. Now, why is that special? Because it points only in the x direction, and its magnitude is the square root of 1 squared plus 0 squared plus 0 squared, so the magnitude equals 1. So the magnitude of I hat equals 1. That should be an equal sign. Let's make that clear, because that's pretty important. Equals 1. And then there's another one called j hat. J hat equals, as you might guess, it doesn't go in the x direction at all, but it does go in the y direction, and it doesn't go at all in the z direction. Likewise, the magnitude of j hat is also going to be 1, 0 squared plus 1 squared plus 0 squared. Finally, the vector k hat, I bet you can guess what this is, doesn't go in the x direction, doesn't go in the y direction, but it does go in the z direction. That's k hat. So in 2D, we can write some vector p as the vector 4, 5, but that's exactly the same as saying 4i plus 5j. 4i plus 5j is the same as 4, 5. Why is that? The x component here is 4. That means it's 4 times this unit vector I. We scale this one up. The I points only in the x direction. We're going to make it 4 times as big. Oh, sure enough, it's 4 in the x direction. This is a unit vector in the j direction. It points up 1, and we scale this by 5, so it becomes 5 in the up direction. Okay, 5 in the y direction. That makes sense. We could do another one. Q is the same as 3, 1, and that equals 3I plus just plain old J, right? Pointing in the up direction. So if I wanted to do P minus Q, that equals 4I plus 5J minus the entire vector 3I plus J. So that will equal 4, we'll just collect the like terms, right? 4I minus 3I, that's just I. And then 5J minus J is 4J. Now, this doesn't seem a whole lot of much of a time saving over just subtracting these directly, but later on you'll find these unit vectors to be pretty useful because we can just keep track of i's, j's, and k's. Now, how do these help us deal with magnitude and direction? More on magnitude and direction. So we've got these vectors here, I, j, k. They're all perpendicular to each other. I is perpendicular to j, j is perpendicular to k, and if you think about it, k is perpendicular to both I and j. They're all perpendicular to each other. I guess I'll start this on a new page. It's 2 pretty weak pages there, but the ideas kind of go together. Now, let's say I've got a 2D vector. Let's call it V because I'm not feeling very creative, and I'm going to say that equals the vector 5, 12. All right. Well, I can also say that equals 5I to take care of the x component, and I'm going to add that to another vector, which will be 12J. Right. Same thing. So 5, 12 is 5A plus 12J. If we think about that visually, it's 1, 2, 3, 4, 5 in the x direction, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the y direction. So this is 5I, and this is 12J. Put little hats there. Okay, 5I plus 12J. Now, we've already talked about how to do the magnitude of this. The magnitude, written as kind of this absolute value sign looking thing, is the square root of 5 squared plus 12 squared, which we know equals 13. It's a Pythagorean triple. That's why I picked 5 and 12. That wasn't random. I just tried to make it sound like it is, but it's not. But what about direction? This is the magnitude. What about direction? So what about it? Well, we remember that we have these other directions. I, points in the x direction. J points in the y direction, Z points in the, or J points in the Z direction, but what points in the V direction? These I ones, I, J, and K are all really nice because they have a magnitude of just 1. They don't really have a length. You can multiply them by anything and the length doesn't change because their magnitude is 1. But what points in this direction? 5, 12 points in a certain direction, but it's got a bunch of magnitude. And we know the magnitude is 13. So we know this one points in the right direction, but it's got some magnitude. So what if I took 1/13 of that? 1/13 of 5I plus 12J. What does that equal? Well, I can just scale this one, except instead of scaling it up, I'm scaling it down. That becomes 5/13 I plus 12/13 j. Now interesting, it had a magnitude of 13. I scaled it down by 13, so I bet the magnitude now is, so let's check the mag, will be 5/13 squared plus 12/13 squared, square root that, and that equals the square root of 25, 1/69, 144, 1/69, so that's 169, 1/69, which that equals 1. So what we have now, this thing here, where to go down here, points in the same direction as the original vector, but we've scaled it down so it has a magnitude of only 1. Well, that's kind of nice. So that the magnitude of this thing is 1. If I needed a vector, if I needed a new vector, say I want with magnitude of 100, I need a big vector pointing in the same direction, the v direction. Well, one option would be to say, well, the magnitude of this is, oh, I should make this a vector. The magnitude of v was 13, so I'd multiply that by, let's see, 6 would be, what would that be, 88 and 78. So multiply by 7, and that's 91. Multiply by 8, that's 91. No, that doesn't work. So I could figure out what I need to multiply this by to get 100, or I could just take my 100 times the unit vector that points in the same direction. 5/13 I plus 12/13 j. Well, I know the magnitude of this. The magnitude of this is 1. So it doesn't really change the direction of this at all, or it doesn't really change the 100. The magnitude of this thing will still be exactly 100, and the direction will be exactly this. So this is, I'll do this in a different color. This provides, this is direction only, magnitude 1, direction of v, and this scales it. Scales my vector. So magnitude, direction. It's a unit vector that points in the direction that I want. In general, to get a, I lost my, where am I here? There I am. Go back to the black pen. In general, to break any vector into mag and direction, what I can do is say the magnitude, or I take my original vector v, equals the magnitude of v times my original vector divided by its own magnitude. Right? Now you might look at this and say, well, no kidding. I mean, the vector v equals the vector v because these two cancel out. But if I write it, if I leave it like this, this as one entity, just the magnitude, and I multiply this by just the direction, oftentimes this becomes very useful. So I have just the magnitude, just the direction, so it kind of helps me see what things are. Okay, I think we should do just one application, a simple application problem of vectors and using these unit vectors. So application of unit vectors. And at the time and place of recording, I'm in Wisconsin, and it's November, and so that means we're getting ready for a very special season. And I better change this to red because it's time to go sledding. And when we go sledding in Wisconsin, the fastest and most dangerous sleds that we have are these red saucers. So who sits in the red saucer? But some, little kid, and this guy's a little kid because he's got a big, huge melon and just a little tiny body. When he raises his hands up, his hands don't even clear the top of his head. So here's this kid in the red saucer. Now, a problem with the red saucer is they're not very directionally stable. So, for instance, this kid has two parents. One who we'll call Mama, right, represented with an M. Now, if we're trying to get the saucer to go this way, I want, well, let's just say Mama's pulling off to the side this way with it. We're trying to go straight across the page, right, like good math problems usually go. But Mama is pulling with a force of 150 pounds in the I direction, plus, let's say, 30 in the J direction. Right. Mama speaks several languages fluently. She's very good with arts and the humanities, but not much of a physicist. So she's pulling off in this direction, even though we want the thing to go this way. Well, let's just say that this little guy here, let's call him Orange Boy, is, say, his goal to get where he wants to go. This is the goal, is, let's say I just want a force of 200 pounds in the I direction. And then, so the pressure then is on Papa, who we will represent with, for lack of a better color, blue. Papa has to pull in this direction somehow, so that the result becomes just 200 in the I direction. So P is going to be some PXI plus PYJ. Well, if I want these two vectors to add up to be this, remember I can just add up the like terms. So, now for the physics students in the group, you'd be like, oh, if I would have known this a few months ago, or, this is obvious. But if you've never taken a physics class, hopefully you'll find this to be helpful. If I just want the i's to work out, I want it to be 200 I, so I take my 150i, 150i plus my pxi has to equal 200i, right? Because all the x's have to add up to be just this 200i. Well, that means that my px has to be 50 to make that work out. So 150 plus 50 equals 200. And likewise in the y direction, well, wait a minute, I don't have any y direction here. But Mama does. So I've got to say that 30j, that's supposed to be a 0, not a 6, 30j plus pyj has to equal, well, there is no j component here, so that's got to equal 0j. And so that means that py has to be negative 30. So that way the y's cancel out, or the j components cancel out to be exactly 0. The x components cancel out to be exactly 200, or the x components work together, the I components work together to be exactly 200. So we can break our forces down and just work with the i's and j's. So we can, just a very simple example to show that by breaking vectors down into their components, I, j, and k, we maintain their vectorness. Where I lost myself again. There I am. We can maintain the vectorness. This is still a vector, this is still a vector, this is still a vector, but this is only y components, this is x components. Okay, that's it. If you have any questions about this, please ask them in class.